Hello, we are continuing our discussion on the traveling salesman problem. In this lecture, we will solve two examples using the branch and bound algorithm for the TSP, and we will illustrate how we may need to branch into more than two in the branch and bound tree. So let's get started. So let's consider this TSP example with 6 cities. So these are the distances between each pair of these cities are given in this table. Okay, so these you see the distance from city 1 to city 1 is 100. This number is in fact a very big number, m. When you compare this number with the others, the 100s are very large. It means that they represent big m's. They are infinities. And also you see from the distance from city 1 to 3 is also 100. It means that we are forbidding this move. We don't want to go from 1 to 3. Okay, so in order to solve this problem, with the branch and bound algorithm, the first thing is to solve the root node where we relax the subtour elimination constraints and we solve the Hungarian algorithm. I will not go into details. You can just do it. You will just find the row minimums and then you will find the column minimums and try to cover all the zeros with a minimum number of horizontal or vertical lines. When you solve this, okay, let's say this is our root node, and when you solve this root node, we obtain this solution x14, x43, 36, 62, 25, and 51 all equal to 1, and all other decision variables are 0, and the z value is 43. Okay, and again, if we write our table over here, the lower bound, upper bound, and the gap value in this node 0. Okay, so what do we have? The relaxation optimal solution, which is 43, provides us a lower bound. And then, what is our decision here? Shall we branch or shall we fathom due to some reason? And if you look at the solution, we are moving from, according to these decision variables, we are moving from city 1 to 4, then 4 to 3, then to 6, to 2, to 5, and then to 1 back again. So there are no subtours here. This is a feasible TSP tour without any subtours. So, and this is the root node. It means that we immediately fathom this. Okay, fathom by solving, and the best integer value that we have is 43. And you see the gap value is 0. It means that we just solved the problem. We just relaxed the subtour elimination constraints, we solved the assignment problem, and the result of the assignment problem is a feasible TSP tour, and we just stop here, no need to branch. Okay, so this was just a simple example to illustrate how a relaxation can provide us a feasible solution immediately for this TSP. Let's consider another example. Again, on this table here, I'm going to write the lower bounds, upper bounds, and the gaps corresponding to each node. Okay, so our branch and bound tree will start with node number 0. So let me write this is node number 0, which is the assignment problem. And when I solve this assignment problem, I observe that I will not write the variable values, but I will try to write what tours occurred as a result. So there is a tour 1521, and this is the subtour, and there is another subtour 3643. Okay, so it means that there are two subtours in this initial one. and the z value corresponding to this, I'm going to write it here, so this will be a larger branch and bound tree, so I need to write a little bit smaller over here. So I am going to write z value equal to 65 over here. And initially, again, I don't have any feasible solution for this node 0. For a minimization problem, the relaxed problem optimal solution gives us a lower bound, which is 65. The upper bound, current upper bound, is infinite. Okay, therefore we cannot calculate the gap. But for this TSP, finding an initial solution, initial feasible solution, is very easy. But by just ordering the cities, you may end up with an feasible solution, and we can use the objective function value of that solution as an upper bound. So if you want to use it, for example, you can just say that, okay, 1, 2, 3, 4, 5, 6, and return back to 1. This provides an initial feasible solution with an objective function value of 94. So instead of starting with infinity, we can start with 94 as the upper bound, and in that case the gap value will be 94 minus 65 divided by 65 multiplied by 100, which will be 44.6%. Okay, so this is our initial gap value. And since there are two subtours over here, we need to branch in such a way that to avoid these two subtours. So be careful here. In our previous example, the subtours consisted of two cities, but here the subtours are consisting of three cities, each one of them. In the first one we have 1, 5, and 2. In the other one we have 3, 6, and 4. So we will select one of them. Since both of them have the equal number of cities, we can select one of them. Let's select the first one arbitrarily. So we are moving from 1 to 5, then 5 to 2, and then from 2 to 1. Okay, and we need to write constraints in order to eliminate this. So this is x15, this is x52, and this is x21. So which means that we need to branch this in such a way that we avoid this subtour, we prevent this subtour. And we can do it in this way. Either we will set this variable to be equal to 0, or this one to be equal to 0, or this one to be equal to 0. So there are three alternatives. Okay, so be careful here. Don't just memorize the previous examples or the previous traditional branch and bound, but think about it. So it means that in order to avoid these subtours, in order to prevent these subtours, we need to branch this into three. Okay, so the first branch, let me just sketch like this, the second branch, and the third branch. Okay, so in the first branch we will set x15 to be equal to 0. In the second one, x52 to be equal to 0, and in the third one, x21 to be equal to 0. If you do not branch into 3, but if you just branch into 2 of them, then you may miss the optimal solution. You may not guarantee, you cannot say that the final solution is optimal. Okay, that's very important. So this is different than the classical branch and bound that we developed for the mathematical programming based solutions. So for this case, we are branching into 3. Okay, so let's consider this first one, and again we are going to use the depth first search rule. So we have 3 open nodes now, and since all of them are at the same level, we will select one of them, and let's assume that we are selecting this one to be the next. Okay, so it means that in this node, let me just clean this part. In this node, we are setting x15 to be equal to 0. And how can we do this? By basically in the distance matrix we set d15 to be big M, and for big M we used 100. We just change it to 100 and using the Hungarian algorithm solve this problem again. And when you do it, again I'm writing the solution. So there is a switch from 1 to 2, then back to 1. So there is a subtour of 2 cities. And then we have 3, 5, 6, 4, and 3. Okay, so there are again 2 subtours. One consists of 2 cities and the other one consists of 4 cities. So what, and let me write the Z value. Z value is 75. And what shall we do here? Can we fathom or shall we branch? And since we cannot fathom, since this is not a feasible solution, and since this 75 is better than our previous solution, which is 94, we cannot fathom because of bound, so we need to branch. And we can select any one of these subtours in branching, but as I said, we select the subtour with the smallest number of cities. Otherwise, if you select this subtour, okay, then you need to branch into 4 this time, because there are 4 cities, there are 4 transitions, and in order to eliminate this subtour, so from 3 to 5, 5 to 6, 6 to 4, 4, and 4 to 3, in order to eliminate this, you can either eliminate this one, or this one, or this one, or this one. So you need to branch into 4. Okay. Therefore, we use the other alternative to branch, so that we reduce the size of the branch and bound tree. It means that we branch this into 2, basically by setting x12 equal to 0 on this side and x21 equal to 0 on the other side. Okay, now when again, according to depth first search, I need to select one of these 2 new nodes, and I am selecting this one randomly. So let me put these in square brackets, rectangle inside rectangle, so we can identify the node numbers. Okay, so in this one, if you solve this node 2, we obtain this solution 1, 6, 4, 3, 5, 2, 1. Again, how do we find it? By solving the Hungarian algorithm, the assignment problem. And the Z value is 76. By the way, we forget to fill in this table. In node 1, the lower bound is given by the parents of the open nodes. Okay, and the best parent is the root node, which has an objective function value of 65. And until now, we couldn't find any other integer or any other feasible solution, so that the upper bound is still 94. So our gap value is still the same. Okay, now when you look at this solution over here, this is a feasible tour in node 2. It means that this is a new solution, and when you compare this solution with our previous solution, which is 94, since this is better, this is an incumbent solution. We update the incumbent. So we fathom by solving or by feasibility. Okay, so in node 2, the lower bound is still the same, but the upper bound is updated to 76, and the gap value is 76 minus 65 divided by 65 multiplied by 100, and we obtain 16.9%. Okay, so this is the gap value at node 2. Then according to depth first search, I need to select this one as our new solution, and when you solve this one, we obtain this 1, 2, 3, 5, 1, and 4, 6, 4. So there are two subtours. One consists of 4 cities, the other one consists of 2 cities, and the Z value is 77. So what shall we do? Can we fathom because of feasibility? No, because there are subtours. Can we fathom because of bound? And when you look at the objective function value here is 77, and our previous solution was 76, so our incumbent solution is better than this one. It means that there's no need to evaluate this node further, so we fathom by solving. Okay, so when sorry, not by solving, by bound. Okay, so for this node, node 3, lower bound is still 65 because of the parent, because of the root node, and upper bound is still 76, and the gap value is 16.9%. Now we have two open nodes, and they are at the same level, and according to depth first search, we will select one of them randomly. So I'm selecting this one as our next node. Okay, and when we solve this problem, we obtain this solution 1 to 5 to 3 to 1 to 2 to 1. This is one solution, and 4, 6, 4, the other subtour. Okay, and the Z value is 67. Now question, can we fathom because of feasibility? No, there are subtours. Can we fathom because of bound? Our initial best solution, previous best solution is 76, but this one is 67. It means that we can obtain a better solution here. So we cannot fathom because of bound here, and we need to branch. And since there are two subtours, we need to select one of them to branch. Since this second subtour over here has 2 cities, we are going to use that subtour to branch, which means that we are going to branch into 2. Okay, so on this side we will set x4, 6 equal to 0, and on the other side we will say x6, 4 equal to 0. You see, in this branch and bound 3, at the first level we branched into 3, and in this second level, in these nodes, we are branching into 2. So there is nothing standard here. You can use, or you can branch into 3 in lower levels as well. So it all depends on which subtours, or in your subtours, how many cities do you have. Okay, that's for you need to be careful. That's why you need to be careful. Okay, now according to, let's write what we have in node number 4 first. Our lower bound is still the same, and our upper bound, the best integer solution is still 76, and we have 16.9% as the gap. Now, according to depth first search, I need to select one of these two new nodes, and arbitrarily I'm selecting this one. And when we solve this problem using the Hungarian algorithm, we obtain this solution 1, 2, 3, 5, 1, and 4, 6, 4. You see again, sorry, I made a mistake here, sorry. So the solution that we obtain here is 1, 5, 1, and 2, 6, 4, 3, and 2. Okay, again we have two subtours, and the Z value is 72. We have two subtours, One of them consists of 2 cities, the other one consists of 4 cities, and we cannot fathom because of feasibility. Can we fathom because of bound? The solution value 72 is better than our incumbent solution 76, so we cannot fathom. It means that we need to branch. And again, since the smaller subtour has 2 cities, we have to branch into 2. Okay. And now in node 5, the lower bound is still 65 and the upper bound is still 76, and we have 16.9%. Okay, now we have 1, 2, 3, 4 open nodes, and according to depth first search, I need to select one of these 2 in the lowest levels. Okay, so I'm selecting this one as my next node. Okay, now if we solve this problem, we obtain this solution 1, 2, 6, 4, 3, 5, and 1. And the Z value here is 80. Okay, but when you look, this solution is a feasible tour. Okay, there are no subtours. Because of that, we can stop here. And also, when you look, the objective function value of this one is worse than my previous incumbent solution. So it means that you don't need to update the upper bound. So what do we have? We need to fathom by some. You can say both solving, fathom by solving, or by bound. Okay, both of them are valid here. So in this branching, we in fact branched. We set x15 equal to 0 on this side and x51 equal to 0 on the other side. And in this node number 6, our lower bound is still 65 because of the root node, and our upper bound is still 76, and the gap value did not change. It is 16.9. According to depth first search rule, we have node number 7 over here, and when we solve it, we obtain this solution 1, 5, 3, 6, 4, 2, 1, and its Z value is 75. Okay, so when you look at this solution, there are no subtours. It means that we fathom by solving here. And when you compare the Z value with our previous incumbent, we see that this is a better one, so we update the incumbent. So in node number 7, we still have the same lower bound, but the upper bound is 75 now. And the gap value is 75 minus 65 divided by 65, which is equal to 15.4%. Now, according to depth first search, the next one we should select is this node over here. And when we solve it using the Hungarian algorithm, we obtain 1, 5, 3, 4, 6, 2, 1. And the Z value appears to be 73. Okay, and since there are no subtours here, we need to fathom by solving. And when we compare this Z value with our previous incumbent, which is 75, we see that this is better. So in node number 8, the lower bound is 65. The upper bound appears to be 73, and the gap value is 73 minus 65 divided by 65, which is 12.3%. Now we have only one remaining node, and we number that one as node number 9. And when we solve this, we obtain this solution. Let me write it here: 1, 5, 2, 3, 1. This is one subtour, and 4, 6, 4. This is another subtour, and the Z value is 67. And since we have subtours here, we cannot fathom because of solving, because of feasibility. And since the Z value is better than our previous incumbent solution, we cannot fathom because of bound. So we need to branch. And since in one subtour we have 4 cities and in the other one we have 2 cities, we need to branch on the smallest one. So it means that we need to branch this into 2. I'm going to branch like this into 2, and on this side we will set x46 equal to 0, and this side we will say x64 equal to 0. Okay, so now we have 2 open nodes. In node number 9, the lower bound is given by the parent of the open nodes, which is 67, and the upper bound is 73, and the gap value is 73 minus 67 divided by 67, which is 8.9%. Now we select one of these randomly because they are at the same level. So we select this one randomly, and when we solve this problem, we obtain this solution: 1, 5, 2, 6, 4, 3, 1. Okay, and the Z value is 70. Since there are no subtours, we fathom by solving. Okay, and when we compare this Z value with our previous incumbent solution, we see that this is a better solution. So it means that in node number 10, the lower bound is still 67 because of the parent of the open node. The upper bound is updated to 70, and now we have gap value 70 minus 67 divided by 67, which is 4.5%. And finally, we have this open node. We set it as node number 11. And when we solve it, we obtain 1, 5, 2, 3. So I'm continuing here. 2, 3, 4, 6, and 1. And the Z value is 70. There are no subtours, and the Z value is equal to the previous incumbent solution. So you can say both fathom by solving, or you can also include fathom by bound, because this Z value is identical to our previous incumbent. It just indicates an alternative optima. So these two solutions are alternative optima. So you can select any one of these two solutions, this one or this one. And in this node 11, there are no open nodes, which means that your lower bound becomes equal to your upper bound and the gap value becomes 0. So the branch and bound algorithm stops, and the last point that you updated your incumbent is your solution. So as I said, this solution over here and this solution over here, both of them have the same total distance value, and they are both optima. They are alternative optima. Okay, so what we should understand from this example is this is different than the branch and bound may be problem specific. For this traveling salesman problem, we developed such a branch and bound algorithm. You may develop other versions. Even for TSP, you may have a different type of branch and bound algorithm. So we can divide this branch and bound algorithm as the classical mathematical programming based branch and bound algorithm, which we did until now. Or we can say problem specific branch and bound, which are these examples that we are solving for the TSP. For any problem, for example, set covering problem, for example, machine scheduling problem, facility location problem. For each kind of these problems, you may develop such branch and bound algorithms that is specific to that problem. So this alternative that we are using to solve for TSP here, the idea that we are using here. It is not directly applicable to any other problem. It is specific to the TSP problem. Okay? So this is, therefore, we call it a problem-specific branch and bound algorithm. And what you should need to be careful about this algorithm is different than the classical mathematical programming based branch and bound algorithm. We may need to branch into 3 or 4 or more branches in the tree. In classical branch and bound, we were always branching into 2. Okay, so you should be careful about this. And in the same example, as you see in this one, in the same branch and bound tree, we may branch into 3 and 2 at the same time at different levels. And the basic idea in this branching is we want to avoid the subtours. We want to prevent the subtours by these branching. And depending on how many cities are there in a tour, in a subtour, we may need to branch into that number. Okay? But the idea of lower bounds, upper bounds, calculating the gap is the same. Okay? So please try to understand this example, work on such examples by yourself, try to better understand this branch and bound for TSP.